Hello, welcome to your OSL640 Week 4 Lesson 1 video. So today we're going to be looking at number representation and number conversions in our Lesson 1 video, and Lesson 2 is going to look at file permissions and how we can use our number conversions and data representation things that we learn in this first lecture in file conversions. So here's everything we're going to look at. We're going to look at converting between decimal, binary, octal, and hexadecimal, and why we want to do this, and some different methods for doing this. When we're dealing with computers, and this should be no new surprise for most of you, data is all stored and represented at some point as binary, or some representation of binary, using different voltage levels. If we're using electromagnetic, Ethernet cable, for example, if we're sending data out over a network, or even within the computer itself. If you're using wireless for communications, it's different radio signals that deal with that, and if we're using fiber optics, of course, it's light. Can represent two states, 1 or 0, on or off. So all of these are just different representations of binary, right? And computers' jobs are to understand what those bytes represent, whether they're characters, whether they're variables, whatever they are. And it's useful for you to understand how this is working, and you're going to look at this in your NWK, I want to say 600 course as well. We're going to be dealing with number conversions. So why do we need to deal with this? Why is this an important thing to learn? Realistically, you're probably not going to use a lot of this every day, but it is needed in certain things. You need to be able to convert between decimal and binary for subnetting, which is what you're going to be learning in NWK 600 in and about, I don't know, the next couple weeks. Maybe now. I know it falls somewhere in your curriculum there. When you learn web design, if you learn anything about web design, you are going to need decimal to hexadecimal for your hex color codes in CSS. And in this course especially, we're going to be looking at binary to octal for setting file permissions in Unix and Linux. So before we know more about number conversions, it's best to understand the different numbering systems first, because they all represent things a wee bit differently. So looking at humans, well, this is kind of where the decimal system evolved from. This is the one that we use, that we count in every day. It contains digits of 0 to 9. It's referred to as a base 10 numbering system. And this is likely because if you hold down your hands, assuming you're not missing any digits on any of your hands, you're not missing a finger or a thumb or anything, we have 10 digits. We have 8 fingers and 2 thumbs, which gives us 10. Computers have circuits that represent data in different voltage numbers, meaning they have possibly 2 states, 0 or 1. This gives us a base 2 system. So each place value, whereas our decimal system, our place values are 10 to the power of whatever digit it's in, whatever place it's in. With binary, it's 2 to the power of whatever place it's in. So 2 to the power of 0 is your first digit, which is 1. 2 to the 1 is 2. 2 to the 2 is 4, and so on and so forth. As we move from right to left, we increment 1 power. Hexadecimal and octal are very similar. They're just hexadecimal is a base 16 and octal is a base 8 numbering system. Same concept, just different base. So with octal, we'll look at first. We deal with each bit represents, well, we'll look at converting in a minute, but within octal we have 8 to the 0, 8 to the 1, 8 to the 2, and so on and so forth as we're counting up. Hexadecimal is kind of funny because as we get, once we pass 9, once we hit 10, we start using letters. So 0 through 9 are the same, but 10 becomes A, 11 becomes B, 12 becomes C, 13 becomes D, 14 becomes E, and 15 becomes F. And you're going to learn different methods for converting between these. Based on the context that you're using, you're going to have to be able to convert between these. You're also going to need these for your quizzes, your test. There is no final exam, of course, but quizzes and tests. And you're going to have to show your work. You don't have to use the exact same technique that I show you, but I need to be able to understand it when I'm marking it. So let's look at one method here. Converting a binary to a decimal number. Your steps are, first you should write down the number. And then starting from the left side, well, we can do things this way. We can do I don't like this method. I'm going to tell you the way I do it. Write out your number. No, this is right. Sorry. Write out your number. I was thinking binary to decimal. It's been a long day. So yeah, start from here, and each one is 1 times 2 to the power of whatever we're in. So this is going to be 1, right? This one's going to be 8. These are, of course, zeros because there's nothing there. This one is going to be a 0. This one's going to be a 0. This is 1 times 64. So we have 64, and 1 times 128. So then you take your numbers, you add them all up. Now you can start to do this fairly quickly once you get the hang of it. But this does get more complicated as your numbers get bigger. So let's show you some binary to decimal conversions. And I have a document set up for this that could be useful. So we're going to take this number here, and we're going to convert it to decimal, which I don't actually have a place for that here. I'm just going to write it up there. So our binary number is here. So we have our first one is, give me a second. Just wanted that over there. Our first place value here, of course, is 0 times 2 to the power of 0, which is going to give us 0. Next over is what is going on here? 0 times 2 to the power of 0. There we go. We have a 1 here, so that's 1 times 2 to the power of 1, which is 2. Uh, 1 times 2 to the power of 2, which is 4. I'll do one more here, and then I'm going to move over a column. 0 times 2 to the power of 3, so that's 2 to the power of 0, 1, 2, 3, which is 0. 1 times 2 to the power of 4, which is 16. And my apologies, you might hear, I don't know if you heard that bing in the background from my email. I heard it. 0 times 2 to the power of 5, which is of course 0. And then finally 1 times 2, so it's 0, 1, 2, 3, 4, 5, 6. I just wanted to make sure I'm counting right. To the power of 6, which is 64. So then we take our values here, we add them up. So we have, I'm going to use a calculator for this, just to do it quickly. You should not do what I say, not what I do in this case. So 64 plus 16 plus 4 plus, whoops. This gives us 86 in decimal. Make sense? Hopefully. So we've looked at binary to decimal. Now we need to look at the reverse, decimal to binary. So this one gets, again, tedious as you do it more. We just write down our decimal number first. We look for our highest bit value that we can subtract that out, or subtract out of that, and we just keep subtracting down to 0 until we have nothing left. And as we're subtracting out, you put a 0 where you didn't subtract anything, you put a 1 where you did. So move all the way down. You can add your leading zeros if necessary, but really leading zeros can be assumed. It's the trailing zeros that matter. Let's have a peek at doing one of those. So for this one, we're going to do 105. So I've got my powers of 2 over here. You can memorize all these if you wish, but I'm going to show you the easiest way to remember them. And that's, I found, to remember benchmarks. So I remember 2 to the power of 10 and 2 to the power of 20, and then I can work my way up and down accordingly. 2 to the power of 10 is pretty easy to remember because it's 1024, which is, that number comes up a lot in computing. So if we need 2 to the power 11, well, we just double that, which gives us 2048. Also a fun game to play on your phone. If we need half that, that's 2 to the 9 is 512. So you can, if you remember this, you can just work your way up and down from there. Of course, 2 to the 0 is 1 because anything to the power of 0 is 1. 2 to the power of 20 is actually a really cool trick that one of my former professors showed me for remembering this one. 10, 4, skip 1, 5, skip 1, 6, backfill 7 and 8. It's 1,048,576. So if you know that, you can work your way up and down just like you can with 2 to the power of 10. So I worked this out in a sheet and I put it all here just for demo purposes. Usually when I teach this, I'm teaching it in person and I write this out on the board. So if we're converting this to binary, we look for the highest bit value that we can subtract out and still have something, and we're going to subtract right down to 0. So the highest bit value we can subtract out of here is 64. Again, you should not use a calculator for this, but I am going to, just because I don't want an error showing up in my recording, and I want to get through it reasonably quickly. So that gives us 41. I'm just going to space over a bit. So from 41, what's the next highest bit value we can subtract out? Well, that's going to be 32, right? So 41 minus 32 should give us 9. That one's a pretty easy one. Don't need a calculator for that. So 9, what's the next highest bit value we can subtract out? Well, that's of course going to be 8, which is going to give us 1, and then we subtract out 1. And then, starting with the highest bit value, I always start from this side when I'm writing it out. You could do the reverse. We have 64, we subtracted that, so we put a 1. We subtracted 32, so we put a 1. Did we subtract 16? No, we did not. We subtracted 8, so we put a 1. Did we subtract 2? No. We subtracted 1, and we did not subtract 1. Sorry, that should have been like that. 64, 32, 8, and 1. Yeah, so 1, 2, 4, 8, 16, 32, 16. Yeah, worked out perfect. So this is 105 in binary. Not too bad. Again, with bigger numbers, this becomes a bit more complicated. And realistically, in industry, you're going to use a calculator for this. But we are academics. We need to understand the inner workings of this. I skipped ahead and did that. So octal to binary and binary to octal are pretty easy. If we're going binary to octal first, you group your bits by 3s, and then you assign the values 1, 2, 4, and add them up. And if you're doing the reverse, you just break these down into groupings of 3 bits, and then write in appropriate 1s and 0s. So let's take a peek at that. I'm going to take this same binary number that we already have here, and I'm going to convert it to octal. So if I do that, we have 3 bits here. So that's going to be a 1, 2, 4. That's going to be a 1. 1 plus 4 is 5. And a 1 there. We can put in the leading zeros just to make it a little bit easier. So in octal, that is, or base 8, it's 151. And appropriately, we should put something representing that this is a base 8 number. To do the reverse, so if we take an octal number, I'm just going to do over here. Let's look at 451. Let's go for numbers that we haven't used, just to make it a little bit differently. So you can start at the left or the right. 4 in octal, remember we have 4, 2, and 1, so that's going to be 1, 0, 0, right? 6 is going to be 4 plus 2, and 2 is going to be 0, 0, 1. And then just concatenate that number together, and we have the binary representation of this octal number. Hopefully that makes sense. We can go over some more examples on Friday's lecture. This one you're going to need some practice with for what we're working on this week. And I skipped ahead and did that. Hexadecimal to binary, very similar to octal, or as octal to binary, and vice versa. We group by 4s instead of 3s, and as we're counting up, anything beyond 9 becomes a letter. So 10 becomes A, 11 becomes B, 12 becomes C, and so on and so forth. So let's look at that same number. We'll do hex to binary and binary to hex. I'm actually going to do the reverse. I'm going to take this and make it as a hexadecimal number. I'm just actually going to leave that one there. So we take our binary here, which was converted from here. We have it in decimal, binary, octal. To convert this to hex, we just group by 4s. Fill in leading zeros if you need to, and we assign the values 1, 2, 4, and 8 to each group of 4. So that's 1, 2, 4, 8. That's going to be 9. And this is 1, 2, 4, and 8. So that 2 plus 4 is 6. So that's going to be 69 in hexadecimal. To go hexadecimal to binary, it's just the reverse of that. So let's pick a number. Let's do 7E3. So to convert this to a binary, you would, starting with, you can go left or right, doesn't matter, just keep them in order. So 7 is going to become 1, 1, 2, 4. So 1, 2, 4, right? E is, I gotta think for a second, 14. So we need to convert 14 into binary now, which is 12 plus 2, so that's going to be 1, 0, 1, 0, right? 1, 2, 4, 8, no, that's 8. 8 plus 4 is 12, plus 2. There we go. That's better. 1, 1, 0, 0, 0. And then 3, of course, is 0, 0, 1, 1. So 7E3 becomes this when we concatenate the number together. 0, 1, 1, 1, 1, 1, 1, 0, 0, 0, 1, 1. Not too horrible. If you have to do octal to hexadecimal and hexadecimal to octal, the method we recommend at Seneca is to use binary as a bridge. So convert your number to binary first, and then you can convert to the other just as we just did. So octal to hexadecimal, hexadecimal to octal. Let's have a look at some of those. I'm going to have to clean up my sheet a little bit, I think. So let's get rid of that. Let's get rid of that, and that, and that, and that. It's going to clean everything up so we can start fresh. So let's do octal to hexadecimal first. So octal, we're going to do that one to a hexadecimal, and we're going to do that one to octal. So first thing we're going to do with this one is convert it to binary. So remember, it's a hexadecimal number, so each one of these is representative of 4 binary bits. So we're going to group by 3s. So 7 in binary is 0, 1, 1, 1. We technically don't need that leading 0 because it is the leftmost digit, but we're going to need them here, so I'm going to leave it in. 6 is going to be 0, 1, 1, 0. And 4 is going to be 0, 1, 0, 0. So we can bring that together, and we have our number here. Now we want to convert that to octal. So we need to take those and group them by 3s, like such. So this gives us 2, 5, 4, oops, 4. Not too bad. Hopefully that makes sense. Again, if you have any questions, bring them to Friday's class. The other way now, we have a hexadecimal number. We're going to take it to octal. So first we convert to binary. So F in binary is 111111. That's the most you can get with 4 digits. F is all ones. 1 is going to be 0001, and D is 10, 11, 12. So that's going to be 8 plus 4, right? So 8, 4, 2, 1. There we go. Now we do the same thing. Group by 3s now. I think I made a mistake on the previous one. Bear with me a second. So that's going to become 7, 5, 1 plus 2 is 3, and that's 4. This one should have become a hexadecimal number. I don't know what I did up there. I'm going to redo this one, just to be safe. So that's octal, right? So that's 7, 6, which is 4 plus 2, and 4. If we want hexadecimal, we group by 4s. Whoops. So we can put in the leading zeros there. So this becomes, that's the downside to doing these off the top of your head. 1, F, 4. So this is this one. This is this one. Hopefully that makes sense, and hopefully I didn't confuse you too much with messing up this first one. At least I caught it. Again, if you need more practice, we can go through some practice on Friday. Also, in Investigation 1, it's all about number conversions. So you can go through that, and that maps to practice questions 1 to 5. So that brings us into the end of our Lesson 1 video. I will see you in the next video. Take care. Be safe.